Hey friends, welcome back to the channel. One aspect of computers that isn't properly understood by software developers is binary numbers. Now I think most people know that computers run on ones and zeros. The CPU in a computer is made up of billions of transistors, which is essentially just a lot of on-off switches. It isn't just the execution of your code that uses binary. It's the storage of your variables in memory as well as the files written to disk. Everything is just ones and zeros in a computer. Before we look at how binary works, we need to look at our existing number system. All our numbers are represented with the digits 0 to 9. So that's 10 characters in total that are used to represent every number from 0 to infinity. You probably remember in school numbers being represented by number columns. So that's your units, which is 0 to 9, your tens, which is 10 to 90, hundreds, which is 100 to 900, and thousands, which is thousands to 9,000, and so on and so forth. The key thing here is we can only put up to 9 into each column. Once we need a bigger number, we then need to move on to the next column. This is what we call the base 10 number system. And in fact, each column is a power of 10. So units is 10 to the power 0, tens is 10 to the power 1, hundreds is 10 to the power 2, and thousands is 10 to the power 3. The maximum number we can therefore store in these four columns is 9,999. So we have 9 in the units column, 9 in the tens column, 9 in the hundreds column, and 9 in the thousands column. Everyone knows the base 10 number system, and it's probably the one everyone uses because we all have 10 fingers. There are, however, other base number systems that we use. Now imagine instead of 10 characters to represent all numbers, we only had 2. And if those 2 characters happen to be 0 and 1, then that is what we call the binary system. If we go back to our 4 columns, in the base 10 number system, each column was a power of 10. In the base 2 number system, it shouldn't be a surprise then that each column is a power of 2. So the first column on the right is 2 to the power of 0, which is 1. Second column is 2 to the power 1, which is 2. Third column is 2 to the power 2, which is 4. And the fourth column is 2 to the power 3, which is 8. If we put 1 in each of these 4 columns, that would be the maximum number we could store. So we have 1 plus 2 plus 4 plus 8, which would be 15. If you include having all zeros as well, that would be 16 numbers that we can store in this 4-column binary system. Binary numbers can also be used to represent characters. In the basic ASCII character set, the first 7 digits of the binary number are used to represent 128 different characters. A, for example, is this, and B is this. The 8th digit is then added to allow for special characters, giving us a total of 256 different characters. It's not just binary numbers that are used in programming. We also use other number bases as well. Emails are usually encoded in base 64, so unlike binary that uses 0 and 1, base 64 will use the characters capital A to Z, lowercase a to Z, as well as 0 to 9, plus, // and equals. Programmers also use base 32 quite a lot as well. The great thing about base 32 is it only uses capital letters and numbers. So it's great for things like file names and URLs where we can't use special characters. And of course, we can't forget base 16, which uses numbers 0 to 9 and letters A to F. And of course, base 16 is also known as hexadecimal, which is most commonly used for colours in CSS. Colours in hexadecimal are written as 3 sets of 2 characters. So the first 2 characters are for red, second for green, and the third for blue. If we look at these 2 characters as a number column in a base 16 number system, then the column on the right is going to be 16 to the power 0, and the column on the left is going to be 16 to the power 1. As we know, hexadecimal goes from 0 to F, with F being 15. So the highest number we can put in this 2-column system would be FF. So we have 15 times 16 to the power 0, which is 15, and then 15 times 16 to the power 1, which is 240, which gives us a total of 255 as the maximum number we can store in this 2-column system. If you include 0 as well, that would be 256 different numbers that can be represented by a 2-character hexadecimal number. If we look at this in terms of colours, then FF with the rest zeros would be red, 00FF00 would be green, and 0000FF would be blue. Given that we know we can have 256 different values and we've got 3 different sets, that would be 256 times 256 times 256 different combinations, which gives us the 16.7 million different colours that you can represent with a hexadecimal colour range. Now, if we come back to our binary numbers, we know that computers store everything as binary. But how does that relate to the different sizes that we have on a computer? Each binary number can have 2 values, either 0 or 1. Now that in a computer is called a bit. So you might have heard of bits before. There are in fact 8 bits to a byte, and then there's 1,000 bytes to a kilobyte and 1,000 kilobytes to a megabyte. Now if you bring this back to programming, a byte is also a data type used in most languages. Now we know that a byte is 8 bits, so a byte is in fact an 8-digit binary number. Again, if we treat these as number columns, we're going to have 8 columns with the leftmost column representing 2 to the power of 7. If we add up all of these columns, then it should be no surprise that the maximum value that we get is 255. Of course, in programming, we don't just use positive numbers all the time, we also use negative numbers as well. Now, an unsigned byte can't represent any negative numbers at all. That's why we have signed bytes. A signed byte can store negative numbers as well, but it can only store numbers in the range of -128 to +127. The reason for this is we need to use one of those bits to represent the sign, and therefore we only have 7 bits left to represent the rest of the numbers. In a signed byte, we use the leftmost bit to represent a negative number. So if it's 1, it's a negative number. If it's 0, it's a positive number. Now, signed bytes use what we call the 2 complement representation. Don't need to worry too much about that. Essentially, numbers 0 to 127 are represented in the same way we have been doing, but for negative numbers, it starts from -128 and starts counting up from there. So if you have 1 on the leftmost bit, then that would be -128. And then we count up from there until we have all ones which represent -1. There are still 256 different numbers we can represent with the 8-digit binary number, but these numbers are going to be from -128 to -1, 0, and then 1 to 127. This is just 8 digits, but of course the more digits we add to the binary number, the larger numbers that we can represent with it. So an int typically takes up 32 bits, which means it's a 32-digit binary number. If it's a signed int, we can store just over 2 billion, but if it's an unsigned int, we can store over 4 billion. Binary numbers aren't just important for understanding the data type sizes in programming, they're also used in bitwise operations. Now, in a previous video, I talked about how and or in an if statement is often represented with a double ampersand or a double pipe. If you use a single ampersand or a single pipe, however, this is actually doing a bitwise operation. If you want to learn a bit more about bitwise operators and binary numbers, then make sure you watch out for my next video and hit subscribe and hit the notification bell so you don't miss it. Thank you for watching, and I hope you enjoyed this video.